Hello. So we are going over unit 9, which is the last unit of the APES material. Very exciting. So to do this, the next few weeks is to finish your unit 9 progress checks. So today we're going to go over, there's 10 sections in unit 9, and it's on global climate change, and LOL that AP thinks this is a 1 unit topic. All right, that's my shade for the day. Okay, so 10 sections here. You can kind of see that we've talked about a few of them. So like the ozone stuff we've talked about, greenhouse gas effect, we'll go over all that. And here is a fun meme that some of us might be feeling right now in quarter 4. All right. So let's start with 9.1 stratospheric ozone depletion. All right. So we know that the stratospheric ozone is that good ozone that protects us, right? And it is being depleted by, if we remember, CFCs from quarter 2. So those are chlorofluorocarbons. And remember, CFCs are completely man-made. So although it's organic because it has a carbon in it, it is synthetic. It doesn't occur naturally. So this is what a CFC looks like. There's carbon, there's 3 chlorine atoms and a fluorine. All right, it is a primary pollutant, which means it's put directly into the atmosphere. It's not created via recombination in the atmosphere. So it's put directly in as opposed to these secondary pollutants. And some sources of pollution are refrigerators, air conditioners, fire suppressants and retardants, and then aerosol spray cans. So those are all sources of CFCs. Now, a large part of why CFCs are so damaging is because they can last in the atmosphere for up to 45 years, which is a long time. And so this is an ozone molecule here, and this is a CFC molecule again. And so we're going to pay attention to these 2 atoms here as I review again how depletion happens, how stratospheric ozone depletion happens. So just as like a reminder that this stratospheric ozone that's further up in the atmospheric column is the good ozone. So this is a high level ozone that absorbs harmful UV radiation, so we're not constantly sunburnt all the time, right? The ground level ozone down here, this is the stuff that is caused via pollutants. So via nitrous oxides and volatile organic chemicals reacting with sunlight, it creates the ground level or tropospheric ozone. But right now we're going to focus on the high level ozone here. So what happens, so this ozone layer up here in the stratosphere is our protector. And so in the past few decades, like I think it was, I cannot remember which decade it was, but a few decades ago, scientists started noticing that there was a giant hole in our stratospheric ozone. So this blue represents the hole, while the green is like that good solid ozone that still exists. So they started freaking out. So how exactly a CFC molecule degrades and like ozone molecules is, so down here we have a CFC molecule. And because sunlight is great at destroying bonds, it'll separate a chlorine atom from the original CFC molecule. So now you have a free floating chlorine atom. Now that chlorine atom bumps into some ozone molecules when it floats high enough into the atmospheric column. And then the chlorine really is then bonds with a one of the oxygen atoms from the ozone molecule. Because remember, the ozone molecule is 3 oxygen atoms. So it's bonded and it's stolen one of the oxygen atoms, and thus now you have O2 and then ClO. So now you have this. And then what you have is then the free oxygen atom releases the chlorine. So it's essentially breaking apart ozone molecules. All right. So when there's like a hole in our ozone layer, like what happens? What is the harm that's caused on us? So one of the things is cataracts. So like intense UV light on people's eyes causes cataracts, or so that cloudiness you might see in like maybe if you have like an older dog or your grandparents or something. And then also, of course, there's skin cancer. So that's a big one. So then the question is like, what is being done about, oops, my animations have failed, but what's being done about the CFCs? So actually the Montreal Protocol of 1987 was a really dope protocol where a lot of nations came together and they agreed to like essentially ban or highly reduce the amount of CFCs being emitted into the atmosphere. So instead they replaced CFCs with HFCs, which are hydrofluorocarbons, and it's still a greenhouse gas, but it doesn't do the damage that CFCs do on our ozone layer. So you can see like this is actually like a happy ending for environmentalism, where it's the ozone had degraded and it looked like this in 2017, which is a big bummer. But it's going to keep closing up and closing up and closing up. So you can see the trajectory, like the total ozone dipped really low in the late 90s, and now it's slowly making its way back to recovery. And it's projected to recover at some point if we keep the CFCs under control, which is awesome. Okay, so that kind of brings us to a little bit more atmospheric stuff. So we want to talk about the greenhouse gas effect. So the greenhouse gas effect is an important one. It is what makes Earth habitable. So it is a good thing. And what happens is there is a layer of greenhouse gases that exist in the atmosphere. And I'll show you a whole list of them in a second, but essentially what happens is they're responsible for trapping heat in our atmosphere. So like the sun's UV rays come in at short wavelengths, and they hit the ground, and then they'll hit these greenhouse gases and they'll reflect in all sorts of directions. But part of it is that they'll reflect back onto Earth, which is great to keep the Earth warm. But if you have too many greenhouse gases, then it's keeping the Earth too warm. So it's necessary for life on Earth, but in non-sciencey terms, it's getting out of hand. So essentially, a different diagram to kind of like help us anchor this this concept is that there's this greenhouse gas layer in the atmosphere, and which traps a lot of heat. So you can see the short wavelengths are coming in, the long wavelengths are coming back. And one thing that happens also is that the amount of sunlight being trapped as thermal energy is also dependent on how much is being reflected back to the atmosphere. So I want you to notice that the sunlight that is being reflected, aka thermal energy that's being reflected back into the atmosphere, are like these ice caps here, or maybe these clouds, but like lighter things that don't absorb sunlight. So like this black t-shirt, if I were to wear it on a hot day, it would be collecting heat, right? As opposed to if I wore a white shirt on a hot day, it would reflect. So the same thing happens on the Earth's surface. We're going to keep that in mind. But the major greenhouse gases that exist that help like trap the heat and reflect light back in are water vapor. And water vapor is less intense of a greenhouse gas because they have such a short residency time. So they're like, they evaporate and then it's rained down again. It's pretty short. Carbon dioxide is a big one. We all know CO2. It's used as a reference point for climate change. Methane, a little of it goes a long way, meaning methane is a very, very strong greenhouse gas. So like releasing any amount of methane into the atmosphere, as their agricultural industry does, it has like larger effects than if you were to release the same amount of water vapor. And then ozone is a greenhouse gas, and so is nitrous oxide. All right. Okay, so the next section, they want to talk about increases in greenhouse gas, and there's a myriad of things that happen when there's an increase in greenhouse gas, but we'll just say we're going to chunk it up to climate change happens. when there's a release of greenhouse gas. Okay, so what are like, let's name two of the things. So there's with the increase of greenhouse gas, with the temperature rises, the ice sheets in the polar regions are going to melt. There's going to be thermal expansion, meaning like when something is frozen or something in solid form, it's going to take up less space than something that is in its liquid form. So like, you know, as the ice melts and it becomes liquid, it takes up more space, right? And that's something I think we'll examine that concept. So then that results in rising sea levels, which is not good for a lot of different organisms that exist on Earth, including us. Also, climate change, due to the excess amount of greenhouse gases, also spread disease vectors. We looked at this last unit, right? When there are places that are becoming warmer and the temperatures are changing, it means different creatures can inhabit that place, and those different creatures are different disease vectors, right? Such as mosquitoes and whatnot. Okay, so all of these things result in the changes of population dynamics that exist, and then also population movement. So it might force, like, if it's forced humans to go to different places, move to different places. It's also forced different species to do so. So increased greenhouse gases, the ramifications, far-reaching, very far-reaching. Global climate change. This is a wildly vast topic. So there are a lot of different effects of global climate change. We're going to stick to the some things that we'll talk about are like the melting permafrost and sea ice. We'll talk about rising sea levels, like we mentioned before, the displacement of coastal populations, marine ecosystems that are affected, ocean circulation and how that affects that, and also ocean currents, or sorry, atmospheric circulation and ocean currents. All right, so we'll touch on those things as a part of the global climate change. That is such a small fraction of what global climate change really is. But to start with melting sea ice. So sea ice are just large pieces of ice in the ocean that exist in the polar regions, like I mentioned before. And kind of like what I mentioned before is that what sea ice serves many purposes. They're habitats, it's a reservoir for fresh water, but one of the things also in terms of the atmosphere is that sea ice acts as like a reflector of sunlight. So on sea ice, about 90% of the heat and the light is reflected back out of the atmosphere. So it has a large cooling effect for the Earth. Only about 10% of it is absorbed. Now, if you didn't have the ice there, you can see that 94% of the sun's rays, the sun's energy is absorbed by the water, and only 6% is reflected. So that's a huge difference. So sea ice has been rapidly disappearing. You can see this image taken aerially from 1979 to 2017. So that's almost like nearly 40 years in time. And you can see the sea ice that exists between all of these mini islands in Canada. The sea ice is disappearing and receding really quickly. So you can imagine all of this space here was space in which sunlight would hit it and then reflect back in the atmosphere. And now I'm assuming you can assume that there's less of this sunlight and thermal energy being reflected in the atmosphere, and thus warming the area more and thus melting more ice. So it's like a positive feedback loop. The same is happening with permafrost. So permafrost is a thick sublayer of soil that remains frozen throughout the year, occurring chiefly in polar regions. So permafrost is the land equivalent of sea ice, where there's actually soil that just remains frozen year round. So when permafrost melts, there's a myriad of things that happens, and how it impacts humans directly right now is that when permafrost melts, the ground becomes less solid because it's a frozen ground that is melting, right? So this happens in civilizations where there's permafrost. Now, there's also the melting of permafrost. It also changes the how water moves across land. So you can see how the melting of permafrost in the bottom area affects the land, but also in particular, I want to draw your attention to the CO2. So when permafrost melts, just like anything, when things are frozen into permafrost, they're frozen, a lot of whatever's in the environment is frozen at that point. So oftentimes CO2 is frozen in permafrost. And so when this permafrost melts, it releases the gases and whatever is left is trapped in there. So there's been a lot of studies about caribou in, I think in like Siberia, like just like huge herds of caribou are dying because there are things that are there are like chemical compounds being released. I can't remember the name of it. In Canada, sorry, in Siberia, that are being inhaled by caribou. And so it's like basically melting permafrost is poisoning them. So that's a huge issue in the polar regions. There's also rising sea levels. So this graph I wanted to show because it says changes in average sea level over the past 250 years based on data from ocean cores. So scientists have collected that this is how sea levels have changed. But you can see right now in the present, it's changing really rapidly, and it has changed in the past, right? But you can see here, that's a huge change that's happening. All right, and there's there, and then I don't really want to talk about that. Okay. So then there's like a lot of ramifications for rising sea levels as, you know, as ice melts and it raises the water levels because you're adding more water in. Coastal communities. So this is like a picture of the Maldives, and like you can see how so much of it is underwater. So if sea levels rise by 9 to 88 centimeters during this century, most of the Maldives island and their coral reefs will be flooded. So another thing to think about other than coastal communities in terms of rising sea levels is also marine ecosystems. And so what happens is, if you remember from the aquatic biomes, a big part of the marine biomes is this continental shelf part, where this is where there's a high biodiversity because there's like so much sunlight coming in. There's a lot of productivity happening, so there can be a lot of biodiversity. And so if sea levels rise, these areas become deeper and deeper, which changes the amount of sunlight that's available. And so you can see in this, it's especially apparent when you look at the photic zone. So like if the sea levels rise up to here, you can see that then there's less and less sunlight being distributed, and it moves, and that damages marine ecosystems that are accustomed or adjusted to a certain amount of sunlight. There's also the changing ocean currents. So the ocean currents are they influence one another, the atmospheric movement. And so global warming could alter ocean currents and cause both excessive warming and severe cooling, depending on the ocean currents, because it influences the temperature of the air around. And so if the ocean currents are being changed, then it's going to change the atmospheric currents as well. So if you remember from Unit 4, we studied about the Hadley cells. And remember, the Hadley cells are very dependent on the ocean, right? El Nino, like such as El Nino and La Nina, right? So if we are if the Hadley cells are being influenced, then there's just going to be there's going to be like currents, like the jet streams that are being altered because of temperature. Right. So then if we're talking about greenhouse gases and the temperatures changing, there's also ocean warming that occurs. So it's caused by greenhouse gases. And it results in a lot of things, but loss of habitat, metabolic and reproductive changes. So you can see here, this is a bunch of coral that's been bleached. So we'll talk about that in a second, but you can see that coral is where it lives at the continental shelf area, and it's a huge hotspot for biodiversity. And so when the ocean warms more and more, the corals degrade, right? So you can see like healthy coral here, severely degraded coral, and nearly dead coral. And we'll talk about that in a second with ocean acidification. So big, long image, but ocean acidification, we just talked about how greenhouse gases, the increase of greenhouse gases in the atmosphere leads to ocean warming. It also leads to acidification. And so when there's more CO2 in the atmosphere from the factories, from the cars, from just like burning fossil fuels in general, it dissolves into the ocean, because the ocean, remember, is a huge carbon sink, if we remember from Unit 4. So it dissolves into the ocean, carbon dioxide dissolves into the ocean, and when it mixes with water, it becomes carbonic acid. Now, carbonic acid is something that is very erosive to calcium carbonate. And calcium carbonate make up most like shell organisms and coral reef. So when there's more carbonic acid in the ocean, it degrades a lot of these organisms' shells in their homes. So you can see in this diagram, you have these healthy looking shells, and then you have these not so healthy looking gangly shells, right? So essentially the hydrogen ions in the acid react with calcium carbonate and deform shells. So ocean acidification has a really high impact. So you can see the deformed shells here. It just like carbonic acid just degrades the actual material. So you can see that it becomes like thinner looking and more frail, and actually the whole thing just looks like kind of wonky. So also the carbonic acid also bleaches coral. So what happens is like the healthy coral, what healthy coral is that there's the structural coral, and then there's an algae that lives inside of it. So this red coral right here still has algae, and so the algae is actually what gives the coral color. Now, a stressed coral, the algae will just kind of leave the coral, and without the algae, it loses its color and also its life. So bleached coral is white. It's got this like eerie, ethereal looking kind of vibe, but really it's just, it doesn't have the living component. It's just like an empty shell, essentially. Okay, so then invasive species. So invasive, first you have to back up for invasive species. There's just introduced non-native. Oh, I don't like the name exotic. Change this. So there's introduced non-native species. So these are species that are not native to an area, but essentially is brought outside by usually by people. So and then introduced non-native species. It's not necessarily that they have a negative effect on the environment. So, however, invasive inherently means there's a negative impact. The species has like a negative impact on the environment, on its ecosystem. So some example, so invasive species oftentimes spread rapidly and also it outcompetes natives and disrupts the food web. So it oftentimes like takes up a lot of resources and leaves less resources for the native species. They're introduced purposefully or accidentally, both happens. And successful invasive species are usually, do you feel like they're K or they are selected? And then are they usually generalists or specialists? So invasive species that are successful are usually R selected, because remember, R selected are the creatures that are usually smaller. They have a type 3 survivorship curve. They invest very little in their offspring. They have many offspring at once. So they're not more efficient, but something along those lines. And then successful invasive species are also generalists. Like they can survive in a wide variety of different conditions, which helps it, right? Helps it spread. And then, why? Because so the question of why is that, our selected species can produce a lot of offspring, don't really have to take care of their offspring, right? And then generalist is that you can survive off of a lot of different things, and usually specialist species are their survivorship is very precarious because they have such specific needs. So an example, this is a very, very interesting species, but an example, in the sea lamprey was introduced in Canada, just all over the North America. It was introduced because of construction on shipping channel canals from the Atlantic to the Great Lakes. So in the Great Lakes, they are currently devastating the trout population. So only 2% of the Great Lakes trout population still exists in there. So you can see how the sea lamprey has affected the fish. Another one is the ornamental plant kudzu. So the Japanese first introduced it to us in the 1880s, and it was also planted. So this was kind of intentional. They just didn't know the full effect of it, but it was useful in as a dust barrier to combat dust in the dust bowl. So the structural parasite on natives, it's up to 500 million lost in forest productivity per year, and it damages buildings and power lines and bridges, etc. So it just spreads really quickly. And then of course pigeons, which are scientifically named rock dove. It was brought in as a domestic pet by early Europeans, but it displaces a lot of native birds because it is a large bird, and it takes up a fair bit of space, and there's a lot of them now. And they're carriers of pests and pathogens as well. Okay, so an endangered species is a species that is very likely to become extinct in the near future. Y'all knew this, but like the endangered species also go extinct for a multitude of reasons, of which are not always man-made. So some natural reasons are like starvation, being outcompeted by another species that maybe just mutated to become its own species, excessive predation, so maybe they have a lot of predators, natural disasters, loss of habitat through natural means, and then impediments to mating. So this is like a picture of a megalodon shark that apparently was an ancient shark that existed, but it went extinct. So what causes endangerment? So there's a couple of things, and one of the acronyms they want you to memorize is HIPCO. So HIPCO stands for habitat destruction, invasive species, pollution, population growth, climate change, overexploitation. And I think they mean exploitation of resources. So these are some things to keep in mind. Okay, so what is it exactly that makes a species prone to endangerment and extinction? So we know from before. We talked about our strategists. And so we can see here some examples of animals. In pandas, it's that they're case strategists. Remember, our strategists usually have an advantage in this. Specializes it niche, which means they're not a generalist species. Narrow distribution, feeds on high trophic level, means they're an apex predator. All of these things make them prone to endangerment and extinction. Okay, so what do we do about all of this, right? What do we do about all of these invasive species, these endangered species? What is it to do? So conservationists have not loved the limitations of the single species approach, because oftentimes in an ecosystem, if there's one species that's endangered, that means the whole ecosystem is just not doing so hot. It's either not supporting them or something is happening there. So protecting habitat instead allows ecosystems to be more flexible and natural. So instead of being like, oh, we got to save like the like red foxes in this ecosystem, like protecting the ecosystem as a whole is generally benefits more organisms and protects species and relationships we're not even aware of. So, and also there is argument that conservationists should be focusing their money and efforts on hotspots of biodiversity, such as like rainforests and coral reefs, rather than places like tundras and whatnot. Just a reminder about the instrumental value. So some intrinsic values of these things are goods and services, recreation, aesthetics, medicine research, genetic info. So these are essentially these are like ecosystem services, right? That all of these different places provide us. Okay, so the last section is talking about biodiversity. And so this kind of feeds nicely from like endangered and invasive species. So this graph kind of shows us like as the human population has increased, so have the rate of extinction in species. And that's not a coincidence. So as we like continue to encroach on their habitats, continue to like mine the resources they need in order to survive, extinction rates have also gone up. Now, to remember HIPCO, because this feeds into the discussion. So what causes a loss of biodiversity in places are factors like habitat fragmentation. So habitat fragmentation is like, okay, so you say you have like a forest area, and habitat fragmentations is when this happens there. So large natural habitats are broken up into smaller, more isolated areas with little to no connectivity. So if there was an organism that lived over on the west side of this green area and they needed to go like every week or every day, they would go over to the east side in order to find food and water and shelter, then they're not able to when we fragment their habitat. Okay, so another reason there is a decline in biodiversity is because there's just the lack of genetic diversity, right? So in wild species, when there's not genetic diversity, it makes them a lot more vulnerable to things like disease, and having less diversity means less protection. So genetic diversity is the variation of all living forms at the genetic level, genes, alleles, or nucleic acid. All right. And then also when something like say for example, something like habitat fragmentation happens, so then you have like, you have an organism that exists over here that only interacts with organisms that exist here, and then there's another one over here. So what happens when you cut a population into these small like groups, inbreeding depression happens. So you can imagine there used to be like 50 of this organism and living in this area, but now it's being like broken down to like 10, 5, 15, like 10. And so then they're having to breed with each other, but there's inbreeding, which lowers fitness. Right, fitness is the ability to like reproduce and like continue the species. And then also inbreeding depression also causes just like less genetic diversity. And so then there's a lesser ability to adapt. All right, so for example, a good example is like the cheetahs. So their population is bottlenecked twice in their evolution history. So bottleneck meaning like they had this population, something happened. So whether that was poaching or a natural disaster happened, so that it shrinks a large part of their population. And so then they lose all of that genetic diversity and they lose just like large parts of their population. And that's happened twice with cheetahs. And so reproduction is difficult for them now. And they're highly susceptible to viruses because once you get rid of such a big part of the population, that also narrows your genetic diversity. So you can see here, like the bottleneck kind of scenario here, where there were a lot of different cheetahs, right? So there's the cheetahs with a lot of different genetic variability, but then when it's bottlenecked, only these survive. And so what happens is there's only these types of this genetic diversity that's repopulating the cheetah population. So you can see here in this graph that population size and genetic variability are very much intertwined. And when both tank, genetic variation is slow to increase again. You can see this is another way that is shown where if a female cheetah mates with multiple males, there's a variability amongst the cubs. So like then if a virus comes through or like some kind of like sickness comes through, then only like one of the cubs is affected, but then the other two cubs are not affected. So they go on and produce more offspring. While then if a female cheetah only mates with one male, so say all the cubs are the same, if there's a virus that sweep through, they're all susceptible for it, right? So that makes their population really vulnerable. All right, and that is all I have for you. So you have for the next 4 weeks to work on unit 9. So hopefully you can pace yourself and finish the progress checks. And this unit is the one that's weighted the heavily on the test. All right, thanks for watching.